So today we're going to look at the difference between a linear and an exponential function. And the big difference between these two is just how they change over time. So a linear function has what we call a constant rate of change, or has a slope. And basically what that means is if you increase the input by 1, these type of functions increase or decrease by the same amount. An exponential function is going to have some kind of a proportional change, or really a lot of times we'll see them talked about as a percentage change. And so let's keep in mind as we go through and we're going to try and write some linear and exponential functions. We've got these two forms that we use. So if we think it's linear, it's going to follow some type of like mx plus b form. If it's exponential, it's going to be this k times a to the x form. So here we have a few different examples, and we're going to try and decide if these are linear or exponential, and then write the function. So for this first one, it says a sports club has 15 members and adds 5 each day. Well, if we let days be the input and the sports club be the output. So let's say C is the club. Okay. And let's let D, the number of days, be the input. Then the club would equal the 15 members plus 5 times each day. This is actually a linear function because we're going up for 5. We're going up a specific number, 5 each day. And remember we talked previously about this being linear. So we could actually, if we wanted to make it look more like mx plus b form, or in this case we've got c and d, I could also say that c equals 5d plus 15. Either one of those would be fine. Okay. B says a bacteria colony has 140 cells and grows by 17% each week. So we've got a percentage growth rate here. So let's let B be the bacteria, or really the number of bacteria. And it's growing each week, so we're going to let weeks be our input. Here I'd say the bacteria equals the initial value, which is 140, times, as we previously talked about, what will we model 17% growth rate with? That would actually be 1.17 raised to the number of weeks. Where'd the 1.17 come from? That's our 1 plus r, if you've forgotten that percentage rate increase idea. A classroom begins with 100 students, but 3 drop out each day. So each day we're losing 3. That is a constant rate. So I'm going to assume this is some type of linear function. Okay, let's let maybe S be our number of students and D be our days. Then our students would equal 100 minus 3 times the number of days. And again, that doesn't necessarily look like our mx plus b form, or in this case we have S and D, but you could rearrange that and say S equals negative 3D plus 100, and now it's in that form. Okay, lastly, a population of 1,750 decreases by 6% each year. So let's let our population be P. And it's decreasing 6% each year, so let's let Y be years. And so I would say P equals our initial amount times a 6% decrease would be 0.94 times, or raised to the number of years. Now I knew this was exponential because again we've got a percent. We're changing by some percentage amount. Now if you've forgotten, where did 0.94 come from? That comes from our 1 minus r, right? Or our 6% would be 0.06, or 1 minus 0.06. That's where that 0.94 came from. Okay, so let's look at a word problem now. A population of deer in 1997 was 15,000. By 2007, the population had grown to 24,000. It is determined by scientists that the population is growing exponentially. Write a function in the form p equals p naught times a to the t, where p is the population of deer and t is the number of years since 1997. So in other words, 1997 corresponds to t equals 0. Okay, so far what do we know? P equals P naught. P naught is always our initial value. In this case, our initial value would correspond to the year 1997, which was 15,000 deer, times a to the t. So we need to somehow find a. We've got this other point, that in 2007 the population was 24,000. That's a point. In 2007, t would be 10, and the population's 24,000. So t is 10 because it's 10 years since 1997. So we're going to use this fact. 24,000 equals 15,000 times a to the 10th. And we've talked previously about how you would solve something like this. What you do first is divide 15,000 over. And so a to the 10th equals 1.6. And then using that TI video about how you simplify or how you find the value of these radicals, we want to do the 10th root of a to the 10th would equal the 10th root of 1.6. So that gives us a equals, and for the time being we're just going to round that to 3 decimal places, 1.048. So now we've got everything we need to write the actual function. P equals 15,000 times 1.048 to the t. So by what percentage rate is the population increasing each year? Well, the percentage rate corresponds to r. We want to think, what does r equal? Well, if a equals 1 plus r, and right now we've got a equals 1.048, then this 0.048, that corresponds to r. That's the amount greater than 1. So we have r equals 0.048. And if we write that as a percentage, because we want to know the percentage rate, that is actually 4.8%. Meaning this population is growing by 4.8% each year. How many deer will there be in 2025? So if we've got a formula, P equals 15,000 times 1.048 to the power of t. All we need to do is think 2025. What t do we want to plug in? Well, in this case, t would be 28. And the reason I'm getting 28 is, remember, we wrote our formula in years since 1997. So the fact that in 2025, we'd be 28 years past 1997. That's how I know t is 28. So we're going to calculate P equals 15,000 times 1.048 to the 28th power. Into 2 decimal places, that gives me 55,745.16. But I would say to round that, because we're talking about deer, I'd say we have about 55,745 deer in 2025.